Okay, well then, let's look at a different problem from different area from physics. The distance problem. So the problem is about figuring out what distance is if you know velocity. So suppose a particle is moving along a line as the time changes between the time A and the time B. So those now have different meaning. Those are values of time. And during that time, you assume that you know the velocity of the particle. And the question is to find the distance traveled. How would you solve this problem? Well, of course, the distance is velocity times time spent, right? So you use this magical formula. Distance equals velocity times the time spent. So time is b minus a. The problem is about velocity, and the problem about this formula is that it only holds if the velocity is constant. Right? So this is true if velocity is constant. And if velocity changes, well, you don't know which velocity to use in the formula, and that's where we have to do some work. Now, what kind of work do we do? Well, we subdivide the time interval into pieces. So we and let's say pieces of length delta t, all the pieces are of the same duration, delta t, and let's say we subdivide into n pieces. And then what we do is we do approximate computation of the distance. So we say that the distance is exactly equal. So let's start with exact equality. The distance is exactly equal to the sum of the distances, distance traveled along the first time interval plus distance traveled along the second. And how do we know that? How do we know this additivity? The distance traveled along the whole time is equal to the sum, equal exactly, right? To the sum of distances traveled along the subintervals added up together. How do we know that? Is that mathematics? Well, when we say it mathematically, it is additivity, it's mathematical property. But how do we know that that holds in physical world? Well, that's physics. And that's what I don't want to deal with, right? The question of why is it that distance equals sum of those distances? The question of why the area is equal to the sum of areas, that's geometry. Although it's part of mathematics, I would still want to stay away from that because we do calculus here. So, here in calculus, we take this as granted, right? We somehow know from our experience, we add distances. And then again, we use this sigma notation just to simplify expression. And then we approximate. So then we do approximation. And how do we do approximation? Well, we say that the distance number I, distance traveled along the short interval number I, what is it approximately? It's approximately velocity, but again, velocity changes, right, during that time. Well, which one to choose? Well, we can choose the starting velocity. Let me call it start time I, multiplied by the duration, right? Or we can say it is approximately velocity at the mid time times delta t, or it is approximately velocity at the end time times delta t. And what makes me say that the distance traveled along the short interval is approximately any of those? It's similar argument as for the area. We assume here, and we now have to speak physics language, right? We assume here that velocity doesn't change a lot during a short interval of time, right? So when we did approximation geometrically, we said that whatever we see looks like a rectangle, and that's the geometry language. Now we say that velocity doesn't change a lot, changes just a little, and that's the physics language. That's the assumption that we make about the motion. It might not be true, right? We don't know that it's true for any motion. For some motions it's not true, but we make an assumption here, and we better know exactly, as we compute further, we know exactly what the assumptions are. But now we assume that velocity stays approximately the same during short time, and then these all approximations make sense. And another approximation is just take velocity at any time, at some time, ti. Sometime during that interval, multiplied by delta t. And then the distance is going to be approximately what? Well, sum of those v of start time times delta t, or it is approximately v of lead time times delta t, and I'm intentionally writing things again and again, because usually people begin thinking when they get tired of writing and writing and writing, right? So let me write it last time. So the velocity at end time times delta t, or it is approximately the sum of v of some time ti times delta t. And at this point I'm so tired of writing that I begin noticing something, right? I begin noticing that what I write here is very similar to what I wrote there. And the answer to my problem, this distance, is going to be equal to the same kind of limit. So for the distance problem, we can express exactly the same hope. We can hope that the limit of those sums, of each of those sums, exists. Moreover, we hope that limit of this sum is equal to the limit of that sum, is equal to the limit of that sum, is equal to the limit of that sum. Again, if that holds, if that happens, then we say that the distance traveled is equal to that limit. Limit as delta t goes to 0 of sums of v of ti times delta t.